Pluto is the only planet, dwarf or otherwise, in our entire solar system that humanity has visited exactly once, not twice. Not with a series of follow-up probes the way we did with Mars or Jupiter. Once. A single spacecraft flew past it in 2015, took a few days of readings, and then kept flying, never to return. And in the years since, NASA has repeatedly studied the idea of going back, drawn up serious mission concepts, and then quietly shelved them again and again. So what's actually going on here? Why does a planet that captivated the entire world just a decade ago keep getting passed over? The real answer isn't laziness or lack of interest. It comes down to a brutal combination of distance, money, and a literal shortage of fuel that most people have never even heard of. Stick around, because by the end of this, you'll understand exactly why Pluto might remain a one-visit destination for a lot longer than anyone would like. And if you want to catch every update the moment NASA makes a move, go ahead and hit follow before we get into it. To understand why going back is so difficult, you first have to understand just how remarkable it was that we got there even once. Pluto sits roughly 3 billion miles from Earth, out in a region of the solar system called the Kuiper Belt, a vast ring of icy bodies well beyond the orbit of Neptune. For most of the 20th century, it was little more than a dim smudge, and even the most powerful telescopes on Earth. Scientists knew it was there, they had rough estimates of its size, but the actual surface, the terrain, the composition, the moons, all of that stayed a total mystery. NASA's New Horizons spacecraft was built specifically to close that gap, and it launched all the way back in 2006. It then spent nearly a decade crossing the solar system, using a gravity assist from Jupiter along the way, just to pick up enough speed before finally reaching Pluto in July of 2015. What New Horizons found completely upended what scientists thought they knew about small, distant worlds. Instead of a dead, featureless ball of ice, Pluto turned out to have towering mountains made of water ice, vast plains of frozen nitrogen arranged in strange polygon patterns that suggested ongoing geological activity, a thin, layered atmosphere, and even hints of a possible hidden ocean sloshing beneath its icy crust. Its largest moon, Charon, turned out to be just as strange, covered in deep canyons and a mysterious dark red cap at one pole. It was, by any measure, one of the most successful flybys in the history of planetary science, instantly transforming Pluto from a fuzzy dot into a genuinely complex world worth studying in far greater depth. And that's exactly the problem. New Horizons answered a huge number of questions, and in doing so, it created dozens of new ones that a brief flyby simply cannot solve. Here's the thing, people don't always realize about a mission like New Horizons. It wasn't orbiting Pluto, it was flying past it at tremendous speed, with only a matter of days to gather as much data as possible before continuing onward into deeper space. Imagine trying to understand an entire country by driving through it on a highway at 100 miles an hour, snapping photos out the window as you go. You'd get an incredible amount of information compared to having nothing at all, but you'd also miss enormous amounts of context. You wouldn't see the seasons change. You wouldn't be able to watch how anything evolves over time. You'd only see one side of everything because there simply wasn't time to circle back and look at the parts facing away from you. That's essentially what happened at Pluto. New Horizons could only image roughly half of the surface in high resolution because Pluto kept rotating during the flyby and there was no way to slow down, turn around, and go look at the rest. So almost immediately after that 2015 flyby, planetary scientists started talking seriously about a follow-up mission, one that wouldn't just fly past, but would actually settle into orbit around Pluto and stay there for years. NASA has funded multiple serious studies into exactly this kind of mission. One of the most developed concepts, sometimes referred to as a Pluto system orbiter and more recently nicknamed Persephone, envisions a spacecraft that would spend around 3 years in orbit, mapping the entire surface, monitoring Pluto's atmosphere as it changes with the dwarf planet's extremely long orbital seasons, and studying all 5 of its known moons in detail. Some versions of the concept go even further, proposing that after finishing its work at Pluto, the same spacecraft could use gravity assists from Charon to break free of orbit entirely and continue on to explore additional objects out in the Kuiper Belt, essentially getting 2 or 3 missions worth of science out of a single spacecraft. It sounds incredible on paper, and scientifically, almost everyone agrees it would be an extraordinary use of resources. So why hasn't it happened yet? The first and most obvious answer is distance, and everything distance drags along with it. 3 billion miles is not a trivial trip. New Horizons, moving faster than almost anything humanity has ever launched, still took 9.5 years just to reach Pluto. And that was for a flyby, a mission that didn't need to slow down once it arrived. An orbiter is a completely different challenge. To actually settle into orbit around Pluto, a spacecraft needs to carry enough fuel to brake dramatically once it gets there, which means launching with a spacecraft that's dramatically heavier than New Horizons was, in some proposed designs, nearly 5 times heavier, almost entirely because of how much propellant is needed just to slow down at the other end of such a long journey. A heavier spacecraft needs a bigger, more powerful, and far more expensive rocket to launch it in the first place. And even with the most efficient trajectory planners can design, some estimates for these orbiter concepts put the total travel time before even entering orbit at multiple decades. Some proposals stretch the full mission timeline out to as much as 50 years from launch to completed science, an almost unimaginable amount of patience for any space agency or any group of scientists hoping to see the results of their own work. Then there's the cost. Early estimates for a full Pluto orbiter mission have landed somewhere around $3 billion, and that figure puts it solidly in competition with some of the most expensive planetary missions ever proposed. NASA doesn't get a blank check. Every mission, whether it's headed to Mars, to Europa, or to Titan, or out to Pluto, has to compete for a limited pool of funding, and that competition happens through a process called the Planetary Science Decadal Survey, where the broader scientific community essentially votes on which missions deserve the highest priority over the next 10 years. A Pluto orbiter has shown up in these conversations repeatedly, but it consistently finds itself competing against other extremely compelling targets. Missions to Europa and Enceladus searching for signs of life in subsurface oceans, sample return missions from Mars, and missions to Uranus, which the most recent Decadal survey actually identified as an even higher scientific priority than returning to Pluto. When you only have enough money and enough available launch opportunities for a small handful of major missions per decade, something has to lose out. And so far, Pluto has consistently landed just outside the very top of that list. But even if NASA found the money tomorrow, there's a third problem that's arguably even more limiting than the budget, and it's one that barely gets talked about outside of the space community. Spacecraft heading out to Pluto, or really anywhere beyond the orbit of Mars, cannot rely on solar panels for power. Out at Pluto's distance, sunlight is roughly 1,000 times fainter than it is here on Earth, nowhere near strong enough to keep a spacecraft's instruments and communication systems running. Instead, missions to the outer solar system depend on something called a radioisotope thermoelectric generator, a device that generates electricity from the heat produced by a slowly decaying radioactive material called plutonium-238. This is the same basic technology that has powered nearly every major deep space mission for the last 60 years, including both Voyager probes, the Cassini mission to Saturn, and New Horizons itself. Here's the problem. The United States stopped producing new plutonium-238 back in the late 1980s. For decades afterward, NASA simply lived off old stockpiles left over from that earlier production era, occasionally supplementing it with limited purchases from Russia until that supply option eventually dried up as well. By the time scientists and engineers really started sounding alarms about this in the late 2000s and early 2010s, the situation had become genuinely serious, with officials warning that without new domestic production, missions beyond Jupiter could become effectively impossible. The Department of Energy did eventually restart limited production, but manufacturing plutonium-238 is an incredibly slow, expensive, and technically demanding process, and current annual output remains a small fraction of what a truly ambitious outer solar system exploration program would actually need. Every mission that requires an RTG, whether it's headed to Pluto, to a Kuiper Belt object, or to one of the icy moons further in toward Jupiter and Saturn, has to compete for a limited, carefully rationed supply of this material. A serious Pluto orbiter concept like Persephone would need several of these generators just to keep its instruments running for the full multi-year mission, which means committing a meaningful chunk of an already scarce national resource to a single multi-decade mission. Put all 3 of these constraints together, and you start to see exactly why Pluto keeps slipping down the priority list, even though nobody in the scientific community has lost interest in it. It's not that scientists stopped caring after New Horizons flew by. If anything, the flyby made them care more, because it revealed just how surprisingly active and complex Pluto turned out to be. It's that going back properly, with an orbiter capable of actually answering the questions New Horizons raised, requires an enormous amount of money, a rare and tightly limited fuel supply, and a level of patience that stretches across entire scientific careers, all while competing against other outer solar system targets that keep winning out in the same funding process. There is at least some reason for optimism if you're willing to think in decades rather than years. NASA continues to fund feasibility studies into a Pluto orbiter, refining the concept, testing whether newer, more efficient RTG designs could reduce how much plutonium-238 a mission like this would actually need, and exploring clever trajectory tricks, like using Charon's gravity to help the spacecraft escape into the wider Kuiper Belt afterward, to squeeze more science out of a single expensive launch. Every time the Decadal survey process runs again, the case for a return mission gets a little stronger, built on more data, more refined engineering, and crucially, a scientific community that has spent the last decade poring over New Horizons data and coming up with an ever-growing list of questions only a long-term mission could actually answer. So Pluto isn't being ignored so much as it's stuck waiting in a very long, very expensive line, one where the ticket price is measured in billions of dollars, the fuel is measured in a handful of scarce radioactive kilograms produced painstakingly slowly each year, and the travel time is measured not in months but in the working. Lifetimes of the scientists proposing to go. New Horizons proved beyond any doubt that Pluto deserves a much closer, much longer look. The mountains of water ice, the shifting nitrogen plains, the hints of a hidden ocean, and the strange red-capped moon orbiting alongside it are all still sitting out there, waiting for a spacecraft capable of actually sticking around long enough to understand them properly, rather than catching a single fleeting glimpse and then vanishing back into the dark. Whether that spacecraft launches in the next decade or the one after that largely depends on choices being made right now in funding meetings. And laboratory feasibility studies most people will never hear about. Choices that will determine whether the next generation gets to see Pluto the way New Horizons let this one see it for the very first time, only far more completely. If a story like this, the idea that visiting an entire world just once and then having to wait decades to justify going back, is the kind of thing that genuinely fascinates you, go ahead and subscribe. Drop a comment letting me know whether you think a Pluto orbiter is worth the wait, and stick around, because there's a lot more happening in outer solar system exploration that most people never hear about until it's already underway.